Hello, grade 12s. Happy Friday. Today, we're moving on from conservation of energy. We're going to do our last topic in the momentum work and energy unit, and that is springs. So we're going to talk about another type of potential energy. And this time, we're not talking about gravitational potential energy, but the potential energy stored within a compressed or a stretched spring. So that'll be our topic for today. A few notes. You will have got your report cards, I think, today or this weekend. Let me know if there's any issues with that, if there's anything that I have maybe overlooked or didn't get put into the system properly. If you've got any issues, just send me an email. And another thing is just that we're getting to the end of momentum work and energy, so just expect there to be a sort of assessment next week on this unit. It'll be in the form of a Google form, and you'll have a couple days to do it. It will have a pretty strict deadline, though, because it is a quote-unquote test. So make sure that you're ready for that. And after we do our springs lesson today, you can start to take a look at the review, which is at the end of your homework booklet. Anyways, before we get started on springs, we do have a problem of the day that we're going to do. So I just need to pull up the proper day here. There we go. And share it with you. Oh, I turned on captions. There we go. Okay, so today is Hairball Awareness Day, April 24th, Hairball Awareness Day. So we're going to make our conservation of energy problem about hairballs. So a cat coughs a hairball upward with an initial velocity of 4.8 meters per second from the ground. How high does the hairball go? So you want you to use the conservation of energy concepts that we talked about in our last lesson, and obviously assume that there's no air resistance. So if you want to give that a shot, you can pause the video right now and get it going, and then resume when you're finished. And if you are done now, or if you're struggling, one thing to note is that I didn't give you a mass of the hairball. And that's because we're assuming there's no air resistance. That means that any mass of any object is going to follow the same exact properties as any other. That's kind of just like going back to the hammer and feather problem that we talked about way earlier in the semester. So what you'll notice when you set up your conservation of energy problem, you'll notice that if I'm asking you how high does it go, that means that all of and it starts from, a height of 0. That means that all of the kinetic energy is going to be transferred completely into potential energy because it's not going to be moving at the end. So this is kind of a tricky question because initially you have no potential energy, and then finally you have no kinetic energy. So if energy is conserved, that means that there's no change in energy. So that means 0 is equal to the change in the kinetic energy plus the change in the potential energy. Now, change in always means final minus initial. So that's what I've done here. And then we see that the kinetic energy the final kinetic energy is 0 because it's not moving. And the initial potential energy is 0 because it has no height initially. So all of that kinetic energy gets converted into potential energy. Now we just replace kinetic energy with 1/2 mv squared. We replace potential energy with mgh. And what you'll notice is that your masses, there's a mass in each of these, will cancel. And that's why it doesn't matter whether I told you how much the hairball, what its mass is. So you get 1/2 v squared equals gh, plug in 9.8 for g, plug in 4.8 for vi, and you will end up solving that the height of the hairball is 1.2 meters. So there you have it, 1.2 meters is your answer. That is our problem of the day. And now we will move on to springs. So we'll talk about springs. The first thing that we need to talk about when we're discussing springs is something called, my camera's really out of focus here. Okay, we'll fix this. Is something called Hooke's law. So just give me 1 sec here. I need to make this full screen. And I need to share it with you. And then after I've shared it, I still need to figure out how to make it not blurry. It's just like we're in class right now. How can I do this? Get it to focus on something here. There we go. All right. So yeah, we're talking about springs today, and the first thing that we're going to discuss is Hooke's law. Now, Hooke's law is a law that describes the relationship between the amount that a spring will stretch or compress and the force that is required to do this. So basically what Hooke's law is just quantifying how stiff or how stretchy a spring is, right? So a spring inside of your, mechanical pen is going to have a way different spring constant than a spring that is used in, say, the suspension of a vehicle or something like that, right? So you've got different spring constants for different types of springs. So let's quantify that and let's see how we can turn that into a formula. What Hooke's law does is it just relates the force required to stretch or compress a spring, and it is equal to something called the spring constant, which we have a lowercase k for, multiplied by x. Now, x in this scenario is the distance that it is stretched or compressed. Now, if you go right now and take a look at your formula sheet, you'll see that it's actually negative kx. That's a typo. It should actually be plus or minus kx. Plus or minus kx. And what that means is we're not concerned with it in a vector sense. We're just going to treat it like a scalar. And plus or minus meaning plus whether it is stretched. I mean, it's all relative, but positive could be stretched and negative could be compressed, or the other way around. It just depends on whether you're moving. Again, we're just looking at positive and negative directions. So let's just write out what everything here means. We have got F, which is our force, and we measure that in newtons. And then right here, K, this is a new one. This is the spring constant. I'll spell this wrong. There we go. Spring constant. And the unit of a spring constant is newtons per meter. Newtons per meter. And what you'll notice is when I end up writing out what X stands for, right? X is just the distance stretched or compressed. Distance stretched or compressed. And we'll always measure distance in meters, right? So when we measure distance in meters, then we'll notice that the Newton per meter, the meters will cancel and we end up with just newtons. So again, just showing us that all of our units of measurement will end up canceling out to give us what we need, as long as we're doing it properly. So remember, this just stands for the stiffness of the spring. That's what the spring constant is. I'm going to move my mouse here. So there's our new formula. We don't actually use this form of this formula that often, Hooke's law. We actually take one extra step here to turn it into a formula for the spring energy, and that one we will use a lot more. So we'll take Hooke's law, we'll move it into this little, I'm going to do a small, almost like proof, and we'll come up with a new formula for the potential energy stored within the spring. So we have to just recall a few things that we've done in previous lessons, and one of which being how we can graph. Whenever we're trying to derive a new formula, we usually end up using a graph as the best way to visually kind of represent what's going on. So we'll use a graph here. So spring potential energy. When a spring is stretched or compressed, potential energy is stored within it. This energy can be calculated by finding the area under the following graph. If I were to graph like so, force versus, now normally if I was going to do distance, I would do d, but because above we used x for the distance compressed or stretched, I will use x. So if I was to graph this and the relationship between the two, you'll notice, right, it's just f equals a constant multiplied by x. Well, that's a linear relationship, so our graph is just going to look like this. Okay. Now, if I want to do that, I have to find, in order to find energy, I have to find the area underneath this graph. So this is similar to, trying to find the area underneath an acceleration time graph in order to find velocity, change in velocity. Okay, we're similar kind of concept. We're finding the area under this graph to give us energy. So we've covered something like this before, and we ended up writing it as area is equal to the work. I should have wrote that the other way, so I'm going to do that right now. But when we end up writing out what the area actually is, remember, area is just base times height divided by 2. Base times height divided by 2. Now, in our specific scenario, the base is x. The height is f, and that is divided by 2. So our work is equal to x times f divided by 2. Now what I'm going to do is I'm going to take a different color here, and I'm going to plug in from up here what f is actually equal to, right? We saw above that f is equal to kx. So I'm going to replace this f here with kx, and we'll see that work is equal to x times kx divided by 2. And in its final form of the equation here, we end up multiplying our x's together, and we get that work is equal to 1/2 kx squared. And it's interesting because that ends up looking very similar to what our kinetic energy formula looks like, right? Kinetic energy was just, kinetic energy KE equals 1/2 mv squared. Well, now we're looking at the spring energy is equal to 1/2 kx squared. So this means that the spring potential energy can be calculated using the following formula. We're just going to write it out here. You can go SE, or you can use E with a subscript S. It's up to you. Equals 1/2 kx squared. And this just represents the spring potential energy. And it's energy, so we measure it in joules. So there you have it. There's our new formula that we're going to use. We can also, just before we get to our one, we're only going to do one example today. Before we get there, though, we can also remember or realize that springs are also going to fall under our principles of the conservation of mechanical energy. So from our last lesson, we were talking about how energy is always conserved. You never destroy or create energy out of nowhere. It always just changes from one form to another. Spring energy is another form of energy that is converted between either gravitational potential energy or kinetic energy. So if we remember that E initial is always equal to E final, well, now what we can end up having, if I want to use this way to write it with the SE and the KE and the PE, we have that the spring energy initially plus the kinetic energy initially plus the potential gravitational energy initially is going to be all conserved and equal to the spring energy final plus the kinetic energy final plus the potential energy final. And in most cases, we'll end up having, one or two of these ending up equally in 0 at certain points, and you can just cancel them out. And yeah, so that should do it for our different formulas. Remember, instead of using ones, you can use I's. Instead of using twos, you can use F. And instead of writing it as SE, you can write it as E with a Let's do a quick example here, a pretty straightforward example, and then I will let you try. There's 5 questions that you can do on your own, and you can let me know if you have any questions. A horizontal pinball machine, which obviously in a real sense doesn't really make sense. Pinball machines are going to be angled downwards back towards the paddles. But just kind of assume that we're on like an inclined plane in a sense, and we're just imagining that incline is the actual horizontal. So it just makes our life easier. A horizontal pinball machine has a spring with a spring constant of 450 newtons per meter. If the spring compresses 15 centimeters and the mass of the ball is 25 grams, what is going to be the maximum velocity that that ball can achieve? So first off, what I see here is that we're trying to find what is V2. And don't worry about, for the time being, I would say don't worry about using vectors. Let's just treat it like a scalar problem right now. So the spring constant, that's K. K is equal to 450 newtons per meter. And then we have if the spring compresses 15 centimeters. Let's just say that's positive. Let's say compression is positive right now. So X, that's the compression distance, is 15 centimeters. Now you're all kind of thinking we got to change that into meters, I hope. Okay, we always try to change these into meters. So 0.15 meters. That's where I see a majority of my mistakes is with conversions. Okay, you can be very, very comfortable with using the formulas. You got to make sure that you remember to do conversions when they pop up on tests and exams. And then the mass, another conversion here. 25 grams is not the unit that we are looking for. We want our mass to be in kilograms. So I divide by 1,000 and I get 0.025 kilograms. And then before I shoot that ball, it had a velocity of 0, right? So V1 is equal to 0 meters per second. So that's all the information that we need. That's all the information that we get. Using the conservation of energy, conservation of total mechanical energy, the total energy before is going to be equal to the total energy after. So if the total energy before is equal to the total energy after, that means that the kinetic energy before, we're not concerned with gravitational potential energy because it's just moving horizontally, right? So we're only concerned with spring energy and kinetic energy. So kinetic energy before plus the spring energy before is equal to the kinetic energy after plus the spring energy after. And then there's a couple zeros to cancel out here. The initial velocity was 0. We already said that. After that ball leaves, the instant that ball leaves the spring, there's no more spring energy in that ball. It has all been converted to kinetic energy. And keeping the idea of friction in play, that ball is at its maximum speed right at the moment that it leaves that spring, and it will start slowing down immediately, right? We're going to assume the frictionless surface, so it would just continue to kind of go at that speed forever. But that is the max velocity, is right when it leaves that spring. And right when it leaves that spring, there is no more spring energy in it. That is a very, very key concept. Okay, so no spring energy in that ball anymore. All of that spring energy has been converted to kinetic energy. So SE1 equals KE2. So let's replace SE1 with 1/2 KX squared. And let's replace KE2 with 1/2 MV2 squared. And a couple things cancel here. That's nice. We get a cancellation of our 1/2s, right? The 1/2s both cancel. And I said a couple things canceled. That's it. That's the only thing that cancels. So we have to find what V2 is equal to. So V2 squared is equal to KX squared. And I'm just going to divide by M on both sides. Divide by M, divide by M. And then we take the square root of both sides to get rid of that V2 squared. And we get that V2 is equal to the square root of KX squared divided by m. I just wrote that again, but there we go. So let's solve for that. Put in our values. Our value of k was 450. Our value of x was 0.15 squared divided by m, which was our mass, which was 0.025 kilograms. So there you go. Plug that into your calculator. And if you do, you should get that V2 is equal to 20 meters per second, I believe. I got my answer sheet here. I'm going to double check. 0.15 squared times 450 divided by 0.025 square root of that is, yeah, 20.1. We'll go with 20. Oh, what's our sig figs? 2. So yeah, you might want to just say, how would we do this? 2 sig figs, I guess. Just put in brackets. That's what I want to do. There we go. All right, so V2 is equal to 20 meters per second. That's our final answer. If you have any questions about the 5 spring questions, I haven't been hearing a lot of questions, so I hope that means that it's going well. Or I don't know, I guess it could mean that maybe we're a little bit behind. Let me know if you think I'm going too quickly or if you're having a hard time keeping up or understanding. Reminder that you will have an assessment test for this. It'll probably be a little bit longer than the one that I did for the unit that we did before this, dynamics. But that was just because we were kind of getting near to when we needed to do report cards and it seemed to make sense. We had already done a quiz, so just to do a shorter one. We'll make it a little bit longer, and that'll be next week, okay? Have a great weekend, and I will talk to you on Monday. Monday, you'll have some time to work. You'll have that day to work on the review for momentum, work, and energy. All right, take care.